Applications of the derivative, max and min problems. The derivative has many applications. Depending on the calculus course that you're in, you use some and not the other. In our course, we will be focusing specifically on some of the business applications of the derivative. So we have already started looking at some of the applications of the derivative. I think we're getting pretty comfortable with things like instantaneous rate of change. We've briefly looked at average cost and marginal cost, marginal analysis, and we're going to begin looking at max, min, second derivative, elasticity of demand, and related rates. But all of these things together are going to really revolve around the same concept. It's the whole idea of what is the derivative. And you're going to continue thinking about the derivative as instantaneous rate of change and the slope of the tangent line and how they apply to these business applications. All right, so now we're going to go ahead and look a little bit further at maximum and minimum applications. And here, again, we will be using the derivative of a function. And what we want to think about there is we know that the derivative of a function we've talked about in two different ways, the instantaneous rate of change at a specific value, and we've also talked about it as the slope of the tangent line at a value. So what I'm going to propose for a second is if we just take a look at a curve of a function, it's pretty easy to see the maximum in that curve that I've just drawn, but the other thing that I want you to think about is at any specific value at that maximum, look at what the tangent line is there. The tangent line at that specific point on the function, the maximum, excuse my crude drawing there, but our slope would be 0 because the tangent line is horizontal. So we're going to be using that whole idea as we go to and begin solving some of these problems. Okay, so let's take a look at an example where we want to maximize revenue. A factory that produces iPods computed its demand and costs and came to realize that the formulas are as follows. Price is equal to 100 minus 0.01x, and cost, C of x, is equal to 50x plus 10,000. So what we are going to find is the number of units that should be produced for the factory to obtain a maximum profit, and the price of the unit. Okay, so let's go ahead and start looking at our solution. So the revenue function is going to be quantity times price. And you can see that I've simplified that function to 100x minus 0.01x squared. Really not necessary for Excel, but for my demonstration here, wanted to do that. So next we're going to look at the profit function. The profit is going to be the revenue minus the cost. So very simply, we have our revenue function from above, and we have our cost function that was given to us in the beginning of the problem. I hope this part of the solution is rather self-explanatory. I took our profit function, and then I took the derivative of our profit function to give us negative 0.02x plus 50. And we want to maximize profit, so we're going to set that equal to 0 and solve for x. When we have solved for x in this equation, we have x is equal to 2,500. This means that when the quantity is 2,500, the revenue is at a maximum. Okay, so it's always fun to look at what the graph of a function would look like. This is actually our profit function, P of x, here graphed in blue, and we can see that it hits a maximum up here. And the thing that's really interesting about this is we already know the value of x at that maximum is 2,500. But the other thing that I always think is important for you to visualize is the whole idea of that tangent line right there has a slope that's 0. And, as we start to talk about why we need to set the derivative equal to 0, it really is coming from that idea that the slope of our tangent line at a maximum is 0. So let's go ahead and look at our solution to part B. Here we're going to find the price that is needed to be charged per unit. So we're going to return to our demand function. So in our demand function, we are simply going to substitute in the 2,500 units that we just found, and that was our x value. So as we substitute that back in, it tells us that the price should be $75, and that would give us our maximum revenue. I hope that this screencast has helped with the application of the derivative involving max and min. So let's go ahead and look at our solution to part B. Here we're going to find the price that is needed to be charged per unit. So we're going to return to our demand function. So in our demand function, we are simply going to substitute in the 2,500 units that we just found, and that was our x value. So as we substitute that back in, it tells us that the price should be $75, and that would give us our maximum revenue. I hope that this screencast has helped with the application of the derivative involving max and min.